Again, I just want to welcome you all to our 8th webinar, which is building a recommendation engine on top of AgensGraph. Our today's speakers is Joe Fagan. He is our Senior Director of Pre-Sales. And before I'll hand it to Joe, I would love to introduce our team, and I would like to talk a little bit about AgensGraph. So our teams are located in different locations. We are global. We are in San Francisco. We are in New York. Joe and his team is located in London, and also we are in Seoul, South Korea. So we are growing strong, and we are growing internationally. To give you a little bit background of AgensGraph, AgensGraph is a multi-model database. And as you can see, it can support relational, graph, key document, key value document, and NoSQL models. By saying AgensGraph is a multi-model, it means that at the same time, it can support hybrid query. And by saying hybrid query, it means that you can have different languages in one query. Different languages can be a cipher query, which is a graph query, and also SQL, which is the relational language. So as you can see in this slide, we have an example of the hybrid queries. In the first example, we have cipher in SQL. Our inner query is cipher, and our outer query is SQL. And if you run this query, you can reach out to both models, and you can fetch the data at the same time. And also in our second query, we have SQL as an inner query, and we have Cipher as our outer query. So it's the same process, and you are able to fetch your data from both models. Now, when it comes to AgensGraph, we also have our visualization tool, which is Agents Browser. You can visualize your data, you can analyze your data, and you can apply some graph algorithm. And also you have capability of, as I mentioned, visualize them. And now at the same time, AgensGraph comes with FDW, which stands for Foreign Data Wrapper. You can transfer and import your data from different sources really fast and simple to AgensGraph. So the data can be web data, file data. It can be also big data or from different databases. So as you can see in the process, it's easy data integration. You can do the data management in AgensGraph and also apply any graph algorithm, do any graph analytics. And as I mentioned, Agents Browser, you can do any visualizations for your data. Now, really brief summary. So Joe can explain maybe himself as well. As I mentioned, Joe Fagan is our Senior Director of Pre-Sales for Europe, Middle East, and Africa. He is responsible for shaping pre-sales and technical marketing strategy in the region and for helping customers to create innovative and efficient solution, implementing graph theory based on AgensGraph. Joe Fagan has over 20 years of experience working in this industry, mostly in data and storage. So I'll make it short, and I'll hand the webinar to Joe Fagan. So Joe, how are you doing today?
Really good, thank you, Aya. That was a very, very nice introduction. I'm flattered. Thank you very much. Welcome, everybody. I hope you're having a good day so far. For some of you, it's come to the end. It's 6 or 7 o'clock in Europe, where I am, 6 in the UK, and a bit earlier for our American colleagues and worldwide. So I shall start the webinar by first of all sharing my screen, which we've practiced a multitude of times, forced by AI, I have to say. So, okay, right, so let's start this, this presentation. So first of all, the presentation is about, as you've probably gathered, recommendation engines. And we're going to talk about what recommendations are, very basically, the underlying theory associated with recommendation engines. I'll be using a particular approach, which is called collaborative-based filtering, which I'll explain. Then there's some arithmetic, which isn't too scary. Then I'll show you how easy it is to import data into AgensGraph, in other words, model the data in AgensGraph. Then we'll create the graph, we'll create ratings and similarity edges. Then we'll create recommendation edges, and then I'll recommend some further enhancements to my very, very basic recommendation engine. But everything that's covered today, you will be equipped to go away and create a perfectly functional recommendation engine. I could always benefit from enhancements, but the core technology, the core theory of recommendation engines will be implemented in literally 40 lines of cipher. It could be a lot less, in fact, but for explanation purposes, we'll do the whole thing in a few lines of cipher. So first of all, very briefly, a recommendation system has the challenge to find for each user the product most likely to be relevant. And product can mean playlist from YouTube or Netflix, or content from Facebook or Twitter, or people from LinkedIn or Badoo, or a product from any product provider. And the amazing thing is that from a return on investment perspective, no other small investment in, say, data analytics proper really delivers sorts of return that recommendation engines do. The theory has been alive for about 26, 27 years. And today, 35% of purchases on Amazon and 75% of what we watch on Netflix comes from recommendation systems. In fact, we all know it's actually even higher than that. I mean, if you're sitting scrolling through videos in your Facebook feed, 99% of what you're watching was recommended by Facebook. So we really do find ourselves in a kind of and in fact, it's worth being aware that just about any data analytics or machine learning or artificial intelligence we touch also comes with not necessarily economic, but certainly socio-ethical responsibility as well. This describes the growth of the flat earth community. I hope I don't offend any people on the call who may be flat earthers, but the dream of the World Wide Web, when Tim first started it, we're not in first name terms, I just can't remember his surname. When Tim first, it was about offering people the opportunity to experience a broad diversity of perspectives. But for many, it's become an echo chamber. And it was a great talk given by the original recommendation designer for YouTube, who kind of is almost apologetic that this was a consequence of recommendation systems. So let's use all artificial intelligence with some sense of ethical responsibility. So here we go. Now, trying to put where recommendation comes on this journey from descriptive analytics all the way to prescriptive analytics, it actually comes, it's quite a long way to the right, considering the small investment that one needs to make to develop a recommendation system. So descriptive analytics is just what we have done for decades, using pen and paper and latterly Excel and things like that. And it deals with sums and averages and patterns. And you can see things like, oh, we happen to sell more hats in winter, as a crazy example. And then diagnostic analytics. This is very like a doctor's surgery: descriptive, diagnostic, predictive, prescriptive. But diagnostic analytics is trying to recognize correlations and apply some reasoning to the data. So there's a correlation between temperature and more hats sold. We don't want to imply causation yet. I don't know if you've studied basic statistics and implication, but so there's definitely a correlation between cold and more hats. And then predictive analysis is going to tell us that next winter, guess what, we're going to sell more hats. And just this knowledge here allows us to gear up from a stocking perspective or a whatever else perspective. And then prescriptive analysis about writing the future. So if we could make it colder, my example immediately tumbles down, but it's the easiest I could come up with. If we could make it colder, then we would sell more hats. So this is what prescriptive analytics is. And with the right recommendation system, we can make people buy stuff, steer them towards stuff that they will inherently find interesting. And so how do we know what they're going to find interesting? And there are two basic principles at work. One is collaborative-based filtering, and another is content-based filtering, and they work in a very different way. So in this example here, I have two characters, Alice and Bob. And Bob buys a blue book and a green book, and so does Alice. So they both buy these books here. And then Alice goes off and buys this yellow book. Well, on the basis that Alice and Bob agreed on this book, let's assume for a moment that Alice might, on the basis that she bought the yellow book, it might be a good book to recommend to Bob. And we're leaning on a fundamental principle that fortunately fits into a nugget of wisdom about human behavior, and that is people who agreed in the past will probably agree in the future. And this is encapsulates just one fundamental basic truth about human behavior. And this is what collaborative filtering unearths and takes advantage of. Content-based filtering is entirely different. Content-based filtering needs to know a lot about the content of the product. It needs to parameterize the product. If it's a tune or a song, and it needs to know the genre, the beats, the writer, the author, what kind of music it is, all these things. Similarly for books and any other products, you build up a description of the book. And if Bob buys this book, which happens to be a science fiction novel from 1936 based in Siberia, then we might be able to recommend this other science fiction book based in Russia in 1937, for instance. This has its advantages and disadvantages, of course. Over here, we have what's called its cold start problem. And that is if Bob joins the community or Bob joins as a new user, then I really don't know what to recommend to him. I'll probably recommend the most popular product or something. But over here, the cold start problem is quite simple. If Bob makes one purchase alone, I already have something that I can recommend him. So we have a cold start problem over here, which collaborative filtering fails at. So sometimes you switch on content-based filtering for brand new users and then switch over to collaborative filtering, or a mix of them. But anyway, for existing customers, this is not a problem. It's worth pointing out that on the collaborative-based filtering, how little information is used to create a good recommendation. I know nothing about the books, and I know nothing about the characters who bought the books. I know nothing about Alice or Bob. I don't know their gender. I don't know no demographic about them as well. The only thing I know about them both, which I don't know about either, is that they're similar. So it's about similarity, and we're going to see that we're going to need a way to measure similarity between people who buy products, and we'll see how we do that later. And out pops something really useful just by measuring similarity. And in a lot of machine learning or data analytics, this concept of similarity between products, between people, between this concept of clustering people around some similar set of parameters is a very common theme, and I'll show you the simplest way of doing similarity testing. So the very starting point for a recommendation system is what's called a ratings matrix. And a ratings matrix captures all of the customers down the left. This is a very small matrix. I've got 8 by 10. Normally it'll be the number of customers times the number of products that you have in your portfolio. That will be the size of the matrix. It will also be a very sparse matrix, and sparse means that almost all of the entries are zero. In other words, almost every customer didn't buy every product or whatever. They're almost all unpopulated. And the only place where you have an entry is where a customer bought a product. If you think of Amazon with its almost 1 billion products or 400 million products or something, then you can imagine this is a phenomenally large matrix in this direction. And of course, the number of customers is phenomenal as well. So you need some efficient way to store sparse matrices in a system with tens of thousands or hundreds of products and customers. And we'll see how we can do that. But the game is about figuring out. So now we know how each customer rated each product. And then the next thing we want to do is fill in the blanks. In other words, we want to know what customer, in this example I've drawn here, I don't know how C4 feels about P3, but what I want to do is populate that cell, so now I will know. And I want to do it for every other cell as well. And then if I look along here and I see C4 and the products he didn't buy yet, which is P3, P8 and P9, once I've seen how we might rate those products, then immediately I can see which of those products he would find most valuable. And clearly it's the one that I think he would give the highest rating. And then the next question becomes, well, how on earth am I supposed to know what C4 will think about P3? And the answer is, find customers who are similar to C4 and see what they thought. So the only customers that have evaluated P3 are C1, C5, and C6. So I have some data. I've got a 5, a 4, and a 2. Now, what do I do? Do I average them? I mean, how do I... And the answer is, I really need to consider... averaging them is not good. It's not good. You just come up with a very weak, very poor recommendation system, but a really rich recommendation system that actually bases itself on collaborative filtering is to consider how similar those other customers are to C4. So if C1 is really similar, then I'm really going to value this opinion of 2. And without saying specifically how I calculate the similarity, this is a measure of the similarity between customers that I've calculated. I'll show you how in a moment. And it's pretty symmetric. So C1 similarity to C2 is identical to C2 to C1. In fact, I only need half of this table because it's a mirror image, and I don't need anything down the leading diagonal because C1 loves C2. C1 and C1 are identical, as are C2 and C2. So I really only need half of this. Again, another sparse matrix. Not very sparse in my example. In fact, there's only one hole. Because C3 and C5 have both nothing in common, so we can't draw a similarity between them. Fine, so now that I have the similarity, I can see that C4 here is kind of half similar with C1, not very similar to C5 at all, and quite similar to C7. So what I want to do is I want to value C7's opinion of product 3 more than I value C5's opinion. And a really easy way to do that is multiply the similarity with what the customer thought of the product. So over here, I'm concerned about C4. I want to see what am I going to put in this box here. And here's what I put in the box. I'm going to go to C1 because C1 gave it a 2. And I'm going to multiply the similarity, which is 0.5. That's the similarity between C4 and C1. That's 0.5, which I got from this table, C4 and C1. I'm going to multiply his rating of 2, and I'm going to kind of, bring it along with me, and it's quite valuable. In the case of C5, because C5 and C1 are dissimilar, or only 0.2 similar, here we go, C5, C5, C1, C4, C5. There we go. So it's 0.2. So I'm going to drag along that similarity, and that is the effect of turning down the opinion that C5 has of product 3. And then, of course, in the case of C7, C7 to C4 is quite strong, as we can see in the similarity here, C4 to C7, 7. So sorry, 0.6, that's valuable. I'm going to bring along a lot of that rating of 5s. In other words, what I've really done is instead of taking the average of these 3 ratings, I've taken what's called the weighted average, prejudiced favorably those customers that are the opinions of those customers who are similar to C4, and I'm sort of rejecting the opinions of those that are dissimilar to C4. And then I have to divide by this little thing to do weighted average properly, which is the sum of the similarities. And that just normalizes it to 3.7, which fits between 0 and 5, which is what I wanted, or 1 and 5. So the next question is, how on earth did I come up with the similarity? And the way to do similarity is to imagine that each of these customers is a point in a 10-dimensional space. And the coordinates of that point are, on the first axis is 3, maybe the X, Y, Z, then I run out of names, W. It's 3, 4, 2, 4. See, these are the coordinates of that vector. And then this is C2, and again it has coordinates. And then, so they're pointing in different directions, but how different? And a great way of assessing how different they are is to simply look at the angle between them. So I'll show you what I mean over here. So here I've just taken, because I'm not able to draw on 10 dimensions, I've just taken these first few values here, first three. So for C1, I had a 342, which I've drawn here somewhere here. This is 342. And then for C2, I've drawn 500, which were the first three parameters in the vectors. I look at their lengths, which I do using just ordinary Euclidean distance, which is I square this and square this and square this and add them all up together and take the square root, which is written very succinctly here. So I take each of the thingies. It's written in the denominator, sorry, yeah, the denominator here. So this is the length of a vector. I square them all up, add them all together, and then take the square root. I do the same for this vector here. So this is the product of the lengths. And then for the numerator, I take what's called the dot product. So to find the dot product, I multiply this by this, this by this, and this by this, and I add them all up together. That's it. And so this will give me what's called the cosines, the cosine of the angle between them. And now maybe we remember from our trigonometry days at school, the cosine of 0 is 1. So the cos of the 0 angle is 1, and the cosine of angles that are orthogonal, like 90, is 0. So if these two customers are pointing in vastly different directions in this vector space, then I'm going to return something close to 0 to reflect the fact that they're different. And if they're pointing in generally the same direction, irrespective of their lengths, by the way, it's a really nice feature that you get from cosine similarity. It's irrespective of the lengths of the vectors. In other words, if this vector was twice as long but pointing in the same direction, I would still come out with the same similarity calculation. That's it. That's as difficult as cosine similarity gets. So, and I did that for every single pair and built that table. And I don't want to let the cat out of the bag, but I've already done it now. I just repeat that for every single number here. So I want to populate this number here. I'm interested about how C2 would think about P2. Now, C2 hasn't rated P2 yet, but many other people have. So I have the 4, the 5, the 2, and the 1 from 4 different customers. And rather than averaging these, I take the weighted average. So I'll multiply how similar C2 is to C1 by this value, how similar C2 is to C3 by this value, how similar C2 is to C4 by this value, C2 to C8 by this value. Add them all up together and divide by the right number, the sum of the similarities, and out will pop. I'll be able to populate that cell. And when I've everything populated along here, then I can look along this row and say, oh, you know what? Of the products C2 did not buy, I can identify the one with the highest rating. That's precisely what we're going to do. Fine, and I've shown you the cosine similarity. Now let's, because I know a lot of people are familiar with Excel, I'm going to go through the mechanics of this in Excel rather than Cipher. And once we've done it in Excel, I'll switch over and show you precisely the same in Cipher. And the first thing you'll notice is how dramatically simpler it is. So this is my raw data that I've taken in. My raw data tells me that customer 1 actually bought, not rated, but because I don't have actually rating data, I'm just going to infer rating by the fact that they bought 4 products. So I'm going to say they rated it like some number. So the customer 1 rates P1 by 4, C1, P2 by 7, and so forth. So this is my data, 3 columns, customer, buys, product. I created a pivot table out of this, and this serves as the entry point to my recommendation system. This is all I need. I don't use any other data that's not in this matrix. So this is my raw data here. C1 bought 4 of P7, and C1 bought 7 of P2. Sorry, I said that wrong, but you understand me. Now, I don't have ratings, so I'm just going to make up ratings, and I'm going to say that the one that they bought most of is the one that they preferred. So they bought most of 8, and sure enough, that will be the highest score here. And all I've really done is divided each number by the total for each row. In other words, I've taken the sum of this row, which adds up to 40, and 4 over 40 is 0.1. That's where that came from. And I did the same for every other value there. Now, I'd really like the values to be sitting between 0 and 1. So 1 is the favorite product, and then all of the other products. So I simply divide by the maximum, by the max here to get an implicit rating that sits nicely between 0 and 1, because that's the way algorithms prefer to work, so you don't get ridiculous scaling, and so I keep everything normalized. This is my cosine similarity. We saw the arithmetic before, but here I'm going to take the dot product above. I'm going to take the product of the two norms of the vector below, which are just its lengths. And to calculate it in Excel, fortunately, there's this sum of products function here. And there's also the square root of the sum of the squares here, which I'm using. So this is the numerator here, sum of the products, and this is the denominator. So I do that for everything, populate the whole thing. Of course, I only need half of the table. The rest was just done for completeness. I don't use it. And then I run straight away for my first of all, for C1, I'm going to calculate all the recommendations for C1, then for C2, and then for C3. It's quite tedious, but for C1, for instance, where does this number come from? Well, I'm trying to find out what does C1 think about P1? And the answer is, I think that C1 is going to think the following about P1. It's already thought 4, but let's take one that he didn't buy. So let's take, sorry about this. So the products he didn't buy are this and this. So I'm going to ask, how will C1 think about this product here? What I do is, for each customer, I multiply how that customer felt about the product by C1's similarity to that customer. So let's take an example here. What will C1 think about P2? I care about what C3 thought, so I will take how similar C1 is to C3 and multiply it by how C3 thought about P2. Say that again. I'm going to multiply how similar C1 is to C3, and then multiply that by how C3 thought about P2. So just to confirm that, what I'm doing is I'm taking this value here, which is how similar C1 is to C3. Excuse me. How similar C1 is to C3 here, multiply it by how C3 thought about P2. And I do that for every single product and customer, which there's a value. And then I take these values here and take the weighted average of those, sorry, just the average of those values, and I get the ratings. Now, these are the only products C1 did not buy, starred them, and the recommendation system throws out that of the 2 products C1 did not buy, P7 is valued at a 0.7, whereas P5 is only valued at a 0.25. So clearly this is the product that will be recommended. For C2, it's a little more rich because there are 4 products he didn't buy. And the recommendation system says that this will be the most favored product, P6. Second will be 0.75, third will be 3, and fourth will be 2. And that is that's it all. And now let's have a look at the code here. This is Cypher. I happen to be using VS Code as an editor. This is just Cypher in any editor. I could have used Notepad or something else. This just colors keywords a bit more favorably. So this is the Cypher code, and then I will take my Cypher code and drop it into. I'm going to drop it into AgensGraph. So I just have to start AgensGraph first. The server's already running. This is the command line interface. So this is the command line interface to AgensGraph, and I'll just stick up it's fine. So this is AgensGraph here, and I can see what version of Postgres it's built on. So we're built on Postgres 10.4. And So let's go in here and start copying code in and running it. First thing I'm going to do is just drop all the stuff I created just to start from a clean scratch. Then I'm going to create a table called purchases that's going to have 3 rows. By the way, you can recognize this. This is pure SQL. I haven't written any Cypher yet, but of course Postgres understands SQL and Cypher. That's what we brought to the party. We took the 1.1 million lines that is Postgres and in C. We edited the parser to death and made it understand OpenCypher in addition to SQL. So now we're able to create and modify graphs on almost all OpenCypher commands. So I'm going to create an SQL table called purchases that'll have 3 columns: customer, quantity, product. In other words, it'll look exactly like this table here. That's where my raw data comes from. And then I'm going to copy into purchases from my file. I'm going to copy those rows. I think there's 49 of them. And I'm going to tell it that it's a CSV file. Actually, I exported the other thing to a CSV file, and it has a header. And then I'm going to create. So let's do that straight away. Grab this, drop it into my editor here, and it says it copied 49 lines. So let's say what I dropped. Drop means delete. I dropped old stuff just to start from scratch. So I dropped the old purchases and dropped some other stuff. And now I've already created a table with 49 values in it. And if I select everything from purchases, should not be surprised to see that I have misspelled purchases. And there, obviously, I have all of the data that came in from the purchases file, the CSV file. Fine, let's jump back to my editor and see what else we have. So here I'm going to create a basic graph. Of course, now this command would not work in Postgres. But this is what we've added. So it'll understand create graph. And then I'm going to set the graph path. And then I'm going to create some V labels and E labels that I'm going to call my customer. I'm going to give them the vertex label of customer, and I'm going to create another label called product, which will be called prod, and then I'm going to create an edge label that will join customers to product. And I'm going to label all of those edges with the label buys. And so I'm going to do that immediately. I'll just do that, drop it into my into AgensGraph, and I've created 3 labels, as you can see, and I've also created a graph, set the graph path. So now if I say, show me what the graph path is set to, if I could spell, and sure enough, it's set to basic recommend. So I've created a graph, empty graph, and I've given it a name and switched to it. Fine. Let's go back out. You know what I'm going to do now, just before we move on with this, I'm going to just introduce you to some really, this is the only page I have on Cypher, but Cypher enjoys ASCII Art as a fundamental notation method. And the base notation is I have a customer buys a product or rates a product or whatever. Customer is a node or a vertex in the language. Product is a node or a vertex. They're the same thing. And buys is a relationship or an edge. And in RDF, or triple store, it's called property, believe it or not. We use the word property differently in Cypher. But this is the base notations. You have a node that's connected to another node, which are beautifully described as curly bracket, or whatever, round brackets. And then they're joined by a relationship, which is always described by a square bracket. And then we have a direction of the relationship as well. So here we have node has a relationship, something with another. Nodes go in these brackets and relationships go in these brackets. So for instance, here's labels. Here I'm specifying that I want to refer to things that have the label customer, that are related to things that have the label product. And the relationship is the relationship label buys. Okay, so that just is a generic way of labeling, capturing or collecting just the things that are labeled with these labels. And this then here are identifiers. This XX, which arbitrary, you could say Joe or anything else, is something I can use later on to refer to anything that I've matched in a statement that looks like this. So for specific examples of customer, a particular instance will be labeled XX, a particular product will be labeled Y, and or will be. So if I look for all these, I'd end up having pathways from all my customers to all my products, which I'll show you later on. And this is how we capture properties inside the node. So this here, this is always with curly brackets. So you have name, which is a property and a value. And this is as complicated as a statement really gets. You have an identifier, a label, a set of properties inside curly brackets. This is a full JSON document, by the way. You can have any length. And similarly, unlike RDF graphs, if you're familiar with them, we can have properties, as many as you like, on the edges as well. That's properties and values. So that's your Cipher 101. And if I jump back in here, I think I've done this already, yeah. So now I'm going to create my nodes, and I'm in fact going to create edges as well. So the first thing I'm going to do is I'm going to read each row at a time from the purchases table. So the first row, remember, says C1 bought 4 of P1, I remember. So I'm going to, using the customer label, I'm going to create, merge and create are very similar. I'm going to create a customer node. So its label will be customer. I'm going to refer to it as X for the time being. And its property, we'll have a property called C, and the property will be row.cost. In other words, it'll be C1. I'm going to row and looking at the first value. So I'm going to create a node whose property has a property called C, whose value is C1. So I've just created the C1 node. And I do that for every row in the table that I meet. And I'm also going to create a product. For every product that I meet, I'm going to create a product node. Merge means I want a replication. So there'll only be one C1 node and one P1 node, even though there are lots of C1 and P1 nodes in the table. And then finally, I'm going to create an edge. I'm going to give it a label buys, and I'm going to create an edge between whatever I've identified as customer up here and whatever I've identified as product here. So I'm going to create a link between the X's and the Y's. And I'm also going to assign a property in there called Q, which is the quantity. So once I do all this, then I should have, I've already created, believe it or not, semicolon, I think I do. I've created my graph. I have 18 vertices, 10 of which are products, 8 of which are customers, and I've inserted 49 edges. In other words, I've represented this information here as a graph. So I have my 8 by 10, and if you count it, there'll be 49 entries in there. 49 non-zero entries. Again, it's quite sparse. I only represent the stuff that's got values, which is really efficient, nominally efficient. Okay, so we're going to speed this up a bit now because we've taken that very slowly, but it just shows you how Cipher works. So now I'm interested in rates, and I'm going to do the normalized rating. So each rate, so that the most favorite product will be rated as 1. So I'm going to look for every customer and every product and buys it. I'm going to spin through, find the max, divide each value by the max, and create my normalized rating. So I do that, jump out here and execute it, and then I've created rates vertices. Now, actually, what I did out here as well is if we have Agents Browser product as well, and Agents Browser is a visualization for graphs. So I've created so far. I've created my rates edges. I have both as well, but so for each customer, I have a rates edge going to each product. The next thing I'm going to do is create the little subgraph, which is the similarity. This time, the links will not be between customer and product, it will be between customer and customer. So let's move on and create the similarity edges. All of this green stuff is just commentary. Here I'm going to create the similarity edges. do that. In fact, why don't I display them as well? So do all of this in one fell swoop. So I go to my command line interface, do all of that, and there's my similarity. So C1 is 0.66 to C2, C1 is 0.65 to C3, and I don't really need to confirm, but if I come out here, I'll find I have the same values. So there we go. So now I've created my similarity, and the next thing I want to do is the really easy bit, which is create the recommendation. So for every product and every customer, I'm going to go back, I'm going to multiply the similarity between the two customers concerned times how one of the customers rated the product. If I pick C1 as my target customer to make recommendations to, then I look at the recommendations of all the other customers. So let's do that. Let's do that. And I go here and execute the code. And that creates my similarity edges. So now I've got 80 similarity edges. So not similarity edges, no, recommendation edges. And then what I want to do then finally is I'm going to want to spin through each of those and only display my recommendation where not exists, where the customer didn't. So I'm only going to consider products that the customer has not already bought. I'm going to match X recommends P, and I'm going to sort it by customer and by recommendation. So I'll show the most highly recommended product first for each customer, and that's the end of the code. You can see how simple it is. And here we have the recommendation engine. So this thing churns out, say for example, that C2 or C2, I have a few products to recommend. P6 is a 0.8, P7 is a 0.75. So the favorite is P6. And then if C2 comes online, I will show him product P6 or P7 or P3 or P2, depending on how much real estate I have. And just let's compare that. So that's for C2, did I really recommend P6 at 0.8? Let's just check the arithmetic. So for C2, did I really recommend 6? I did, and then 0.7, and then P3 and then P2. So it seems that what I've done in Cypher seems to mimic quite dramatically easily what I did in Excel. The difference is if I had to do this for a 1,000 by 1,000 matrix in Excel, I'd rather not, or maybe a 10,000 by 10,000. Clearly, I wouldn't be able to do it because each of these boxes has to be built almost by hand because it's so hard to squeeze it into nice Excel. So there you go. That's how to build a recommendation engine. That's how to build a recommendation system. What else would if I had the time and the energy, what else would I do? Well, first thing I do straight out of the box that I didn't bother describing is I'd use cosine centrality on ratings. And the real problem I have is that if somebody doesn't rate a product, in my naive example, I give it a value 0, and that's just wrong. I mean, that's just not valuable. So a much better way is to take everything that has been rated by a customer and drag it down by the average rating, so that you now have negative and positive ratings. So this 0.8 means he really likes the product, and this minus 1.3 means, you know what, he probably didn't like the product at all. We have the same problem with the star system on say, Amazon, 1 to 5. 5 means I like the product. What does a 3 mean? What does a 2 mean? And some users mean different things by it. But because you're able to smooth, harsh, and easy raters, you get rid of that problem of not understanding what 3 means. If a customer very rarely gives a 3 and usually gives a 4 or 5, you know that 3 means he really didn't like it. Whereas if she gives it a 3 but normally gives a 1 or 2, then we can assume the opposite. I'd also categorize the products because there's cosine similarity and collaborative filtering really works in similar category of products. I don't suggest you go all the way to collaborative filtering, content-based filtering, but at least you can categorize your products really simply by what types they are. For consumables, I'd actually show products already purchased. If they're batteries or apples or something like that, they might like to buy them immediately. Again, whereas books and music, you want to show similar but not the same products again. And then to get more sophisticated, I could factor in business preferences. So a lot of vendors want to control their customers' buying patterns. So maybe they're concerned about stock and margin. So for each product, I'd actually have 3 more little boxes, or 4 or n. One about the stock keeping, another about the margin, and another by maybe returns or reliability. And what I would do then is I would the business leaders would decide maybe stock is a big priority this quarter. So I really want to get rid of stock, and it's an absolute priority. So anything that's high on stock, I'm going to rate that product higher. Whereas maybe in a different month, margin is absolute king, and I don't care about stock holding. And so how the business thinks about these things is held in a single array, just one vector, which is how important is stock to me. If it's not important, give it a 0.4 or whatever. If margin's really king, then give this a big number. And the result of this is when I sum all these together and mix it in with how I recommended P1 for a particular customer, then out will come a final recommendation that considers not just collaborative filtering, but also the direction that the business wants to point the organization and establish what it is that's important to the business at any time. Now, this can become a little machine learning problem as well. If you have enough data to look at it, you can divide your customer base into a multitude of segments, play around with K1 and K2 and K3 for each segment, and it becomes then you award by some metric things that are doing well and a cost function, and then you have a gradient descent. If you've studied any of your machine learning stuff, you have a gradient descent problem there to solve, and you could come up with the optimum numbers to maximize whatever it is you're trying to maximize. So there you go. That's what I would suggest next, and that's about the end of the presentation, which gives you 10 minutes back. Over to you, Aya, if everybody hasn't fallen asleep.
Thank you, Joe. Thank you. It was great. So I just want to mention that our chat channel is open. So please, if you have any questions, send it through the chat box, and we'll be more than happy to answer your question. So I'll give it a couple minutes. Please let us know if you have any question.
Maybe I should just share my email address. It's joe.fagan@bit9.net. If you want any of the files that I showed you, either the Excel or the PowerPoint, or indeed the spreadsheet or the cipher code, just drop me an email. I'd be more than happy to send you off those files, and you can create your own recommendation system if you happen to have a matrix to start with.
Yes, and in addition to Joe, you can always go on our website and contact us. We have a tab which is contact us, so it's really simple. You can send us a message, and we'll get back to you soon. Maybe a couple more minutes. It looks like we don't have any question for now. So we might be getting probably question later. So again, if you have any question, reach out to Joe, or you can reach out to me as well, and we'll get back to you as soon as possible. Again, thanks everyone. Sorry, Joe, for joining. Go, please.
I was about to thank you, Aya. Thank you very much for hosting and organizing and everything else. Yeah.
Of course. We'll see you guys in our next webinar. Please wait for our invitation, and we'll see you soon. Have a great day. Have a great day, Joe. Thank you.